am on, right? Yep, there we go. Good morning, everyone. Welcome to the first talk of the day. We got a fun one here. This is Christopher Beacham, also known as Lady Red. She is an artist, a maker, and back-end developer in San Francisco, and she's going to give her talk on visualizing algorithms with Python and programmable LEDs. I will leave it to you.
Thank you. Hi, everyone. I'm Christopher Beacham, aka Lady Red, and let's start. All right, so I figure most people saw this and they thought either one of two things. I want to build my own LEDs. That seems super cool. Or I want to see some fancy blinking lights. And maybe both, but I'm going to try and cater to both audiences. I assume that most people here know some Python, so I'm going to go more into the hardware thing, because that's what I think people won't necessarily know as much about. So, and I'll hopefully at the end of this talk, you'll know where you can go to get started to build this thing that I have right here. All right. So let's begin. So I'm going to start with the hardware. The first thing is people say is what is this thing called? Now, if you search LEDs on the internet, you might find these numbers 3528 or 5050. Those are the names of the actual LED chips themselves, right? So they're actually these things. If you just buy a strip that just says that, then you're probably going to buy a strip that's all one color. It won't be individually programmable. There's no microchip on board. So, and you can tell a lot of the hints of telling chips apart are based on the wires in them. So if you see that this one's got a plus and a minus, and this one's got RGB and plus 24 volts, so there's no data. There's just like a on or off or three values for color. So that's very indicative. So don't get these if you want to program with them. This is a NeoPixel. These are very popular. However, they are very difficult to control with Raspberry Pis. They have, as you can see, they have a data line right here. See, this data line goes this way. However, because they have just one line for data, that clock signal and the data signal have to be combined, which means it's a very, very timing-dependent format. So that's fine if you're using a microcontroller or anything that's relatively simple software-wise, but I want to run Python, which I'm running CPython, and it runs best on like a full computer. So I'm running on a Raspberry Pi, and that's got hardware interrupts, that's got cron jobs, that's got who knows what else happening. And so it can't be there reliably to issue the timing-dependent signals. So you'll have issues if you use this with a Raspberry Pi. There is a library that claims it can do it, but I am skeptical. This is what I'm using. API 102, aka .star from Adafruit. This has got two wires, the data and the clock separately, which means, number one, it's not as timing dependent. You can use just regular SPI to send out. Also, you can change the clock speed instead of being set to 1. So this thing can actually go way higher clock, which is good if you're going to do something that's persistence of vision. That's LED speak for moving around really fast and making an image sitting in midair. All right. So this is what I'm using right here. And it's nice because it can be controlled in pure Python. So if you're going to go buy these, just be aware that each strip has like a bunch of like other names, often like SK something or other, and you have to just be careful because sometimes those are like swap alike. Sometimes you could use those, but other times they'll have slight differences. So just kind of do your research if you see those. All right. So if you're going to buy these things, you'll probably find a number like this in the listings, and there can be a little bit intimidating. So the first one is black or white. That's not the color of the LEDs. That's the color of the circuit board. You probably can't tell, but these are black. Actually, I can't tell. I think they're black. Supposedly black isolates and white like smears the color slightly, but it's pretty subtle. Length is self-explanatory. LEDs per meter. So this is 144. This is the most dense that they make them. And it's very bright. If you're doing like a room lighting effect, 30 is probably fine. And this will affect how much power you need. And then the waterproofing. This is the IP 67. So it could be IP 30, 65, or 67. that just tells you whether or not it's going to be okay to use outdoors. Don't use IP30 outdoors. All right. It'll be like encased in plastic or something if it's one of the higher ones. You also might see these other variations so RGB, I'm going to go into later, but it sucks at making white. The white is really hideous. So they have someone that have like a white LED on board or a warm white on board. I don't have that right here, but if you want to do something and you want to have a nicer white, you might consider doing that. All right, so here's where you buy them from. There's three sources. Amazon can be good prices, but they have a very limited selection. But they ship quickly. I bought this one from Amazon, but they don't have all the options. AliExpress is the next. There's the 3As. AliExpress has a lot of options, but they're often like kind of somewhat sketchy seeming Chinese suppliers. You're never quite sure with the quality, and they often list like this says SK9822 similar APA 102, but like is it going to be similar? You just have to, you have to kind of do your research and it's a little bit riskier, and they also take a lot longer to ship. But the prices are the best. APA 102s are more expensive than NeoPixels, so that's kind of the downside. And then, Adafruit is the other source. Hi, Adafruit. These people are great. They have tons of helpful information on their website, and they also sell a lot of hardware, and you can be pretty sure it's going to be like high quality. But they also have sometimes other options like discs or panels, but they can be a little bit more expensive sometimes. So these are actually all the same strip. This one's $31, this one's $25, and this one is $49. So that's all for the same strip. So you gotta have a couple different options there. All right. So once you've got your strip, next you gotta do is power them. So if you haven't ever calculated power before, I started this and I just wanted LEDs in my room, and I'd only know how to program, so I had no idea what I was doing. Turns out you need to buy a power supply. It needs to be 5 volts, and then multiply the number of LEDs times either 60 or 20, depending on if you want to run them at full brightness. 20 is probably fine if you're going to do like something like this where actually only one LED is lit up at a time. But if you want like full maximum white, you probably want 60 milliamps. And you can always go over. You could just put 100 amps on this thing, and it won't use all of it. But don't switch. 5 volts is what you need. So, that's the kind of thing. So all power supplies actually say how much power they give you. So I just found this out. I was really surprised. So I just thought it was based on what the plug was, but yeah. So if you wanted to use one of these little wall warts, you could probably run 30 LEDs if you're not going to do full power, because that would be 0.6 amps. But you couldn't run them at full power, so maybe you could find a 2 volt or 2 amp wall wart. What I'm using for this, which is more than 30, it's 144 LEDs, is a laptop power supply that I kind of cut into a little bit to make my cord. So don't be afraid to splice and make your own cables. I did all this work at a hackerspace in San Francisco, by the way. If you haven't ever been to a hackerspace, there's probably one in your city, and it's an awesome place to do any kind of hardware or just hang out in general. Yeah, so I'm running this on a Raspberry Pi, if I didn't already say. Here's how you wire it. 3 wires coming from the Raspberry Pi. And we're going to want to pick up, so it uses a protocol called SPI. So we want to pick up, this is the pinout. It shows which pins on the Raspberry Pi do what. And we want the output of the SPI, the clock of the SPI, and then any of these ground pins. So here's a wiring diagram of something similar to how I have it. It's functionally equivalent. This one has the Raspberry Pi being powered from this power. I have it slightly separate, but yeah. So you can set this up. Don't just power the Raspberry Pi and power the strip from that, because you'll burn out your Pi. They're designed for math. They're not designed for channeling power. So, all right. Hopefully that's enough to get you to build this thing. Now let's talk about programming them a little bit. So you might be surprised that not all things that make light can make every different color of light. If you like look at the response of LEDs is different than LCDs. So you might look on your screen and see an HTML color you like, get the RGB value, send it to your LED, and you're going to find that it's not necessarily going to match up. So like for instance, like this is a chart of LCD is this triangle, and then here's all the colors supposedly, and then here's measured LED values. So like this one's supposed to match up to that one, but as you can see, it's actually kind of a different green. So you're gonna get a little bit of a skew with colors like that. Just something to be aware of. Another fun thing I realized is you can't get brown out of this because it shoots out light, and there's no such thing as brown light. You also kind of can't get gray. It just looks like a dim white. You can get black great because you can turn it off, but yeah, so sometimes like the way mixing colors together doesn't work out exactly as you want it. Then the white also. You might, like, I just want you guys to realize this is a piece of hardware and it's not like an abstract any color generator. So the white sucks, and we'll get into that. Another interesting thing about Raspberry Pis, or about LEDs, is that they are really good at having very accurate amounts of brightness. So if you give it like, you know, a 20% duty cycle or a 70% duty cycle, it'll be that much brighter. But our eyes won't perceive it that way because our eyes actually kind of suck at seeing light. Well, it's more like they're great at seeing light, but they normalize everything. So I can be in a room with a candle and see pretty well. Then I can go outside into the daylight, and I won't have my eyes explode because we just take everything and put it on a log scale. So you'll see a dim light is brighter and a bright light is dimmer, which means that if you just do a for loop, like a naive for loop, and just slowly increase the brightness, it's going to look like it's not going to look right. So what I like to do is something called gamma correction that I actually learned on the Adafruit website. And you kind of do an inverse log correction or to the LED so that it kind of brightens more slowly than you actually ask it to. And the result is your eye starts to look sees it correctly. So I actually have a demo of that. The top part will be just a regular for loop, slowly increasing brightness. The bottom part will be the gamma corrected version. So as you can see, this one's already maximum brightness. That was like the first 10 values, maximized brightness. And this one's going to come up much more slowly. So if you know about that, I mean, it's kind of a trick, but it'll let you kind of have a bigger range of brightnesses. Otherwise, they're all going to look the same. All right. Next kind of gotcha that people will encounter with this is you think it's RGB LEDs, RGB, I'm going to program an RGB. But I'm just going to say that you shouldn't, because RGB is very confusing. It's good for telling which LEDs to light up at a certain time, but everything people want to do with color that's intuitive to us is hyper hard to do in RGB. So imagine you want to do like a rainbow fade, like I was showing at the beginning of this talk. To do that in RGB, you have to plot a circular loop in a three-dimensional space to go through this rainbow fade. Whereas that's a really common thing to do. Also, maybe you're here and you want to be slightly like you want that color to be stronger. Then you have to take some fraction of where you are and apply that multiplier to your current vector to get there. The point is, you're going to be doing a lot with confusing vectors if you're in here. Whereas if you use hue, saturation, and value color space, then it's much more intuitive. Hue is just one value that starts kind of in the red and goes the whole way around. So it's really easy to do a rainbow. That's just a for loop. If you want to make them darker or brighter, that's just a change in value. And you want to make them like whiter or less white, that's a change in saturation. So, and then you can just use the library to convert from this to RGB. The strip only ever speaks RGB, so you will have to convert it. Other thing is just that different LEDs are slightly differently bright. So like if if I give you 111 in RGB, then we'll see that it's probably like kind of a sickly bluish green white. Yeah. Yeah. Basically, the white sucks. I'm gonna also show you maximum white. So you might think that this is a nice white to light your house, but really it makes it look like a surgery wing. So, yeah, I mean, you can kind of do something. This is like a more redder one, but if you want to have a really nice white, you might specifically get with a white chip on board. All right. Okay, so let's talk about Python now. So there's kind of two libraries that I'm recommending if you're going to try this out yourself. The first is this Tinui APA 102 library, which is what I started with. It's just a Python, pure Python library that drives these things. And then I forked it and I added, well, I'm a web developer, so everything needs to be a microservice. So I added, there's a client that actually drives the light on the Pi, and then it requests a configuration from a server that could be hosted anywhere. And then there's other kinds of things you can do with it. And I have a lot of different demos. So you can feel free to kind of join this. Right now it's controlling the lights in my bedroom, but it could control the lights in your bedroom too if you'd like. So here it is, or here's a slightly more up-to-date one I deployed this morning. And there's just like a little control panel with all these different schemes, I call them. And here's an example scheme that is in my library. I have a ton of useful helper functions. So this one is the max white that we saw a second ago, the surgery white. So it can be as simple as this. Just set all to one color. All right, I'm gonna show you another. Oh, how about I had another? We'll get to it later, I guess. All right, 1 second. Yeah, I wanted to show this scheme too. So this is a slightly more complicated scheme, as also shows up in my library. I'll turn it on for you so we can see. This is a scheme I wrote to help myself meditate. It will slowly dim and brighten as time passes to indicate how quickly you should breathe. And then it also slowly burns down from the top like a candle burning down to give you like a passive sense of time passing. And I mean, that's kind of complicated, but here it's only like 8 lines of Python. And you don't necessarily have to understand it now, but there's a little bit of math figuring out to figure out how far along we are in the 10 seconds. And then I put it on like a sine curve and set the brightness to that. And then I set some of them dark. Figure out how far the candle should have burned down, darken them, and yeah, and then return true to paint it. And I have a lot of different things. In these schemes, you can do anything. You can hit an API. You can, you can query time. You can query a database. You can do anything because you're completely in Python. Unlike something where you're on a microcontroller, there's a limit to how much resources you can access. But here, you have the world at your fingertips. Okay, so now I'll show you some demos and the visualizations of algorithms. So this one was Perlin noise. It's one of my favorites. If you're not familiar with Perlin noise, it is like a random number generator that has moods instead of so each value is correlated with the next value instead of being completely uncorrelated. But overall, it's still random. This makes really nice mountain ranges and maps, and it's also cool for this because it makes like a slowly, calmingly, slowly changing rainbow. That's one of them. I showed you breathe. All right. The next one I'll show you is this distribution one. It shows us sampling a couple different distributions. So this is a Gaussian distribution, and this is like a little heat map. This one I am using the HSV color space because I wanted to make it slowly get more red as it went on, and that would have been really kind of icky mathematically to do in RGB, whereas it's trivial in HSV. Yeah, so then this is two Gaussians, and there's a couple others on there. The next one I'll show you is a beta distribution. So a beta distribution, my data scientist friend told me about this. It's like a way of estimating the underlying probability of like a coin, and you don't know so you're flipping a coin and you're observing it, and you kind of hone in using Bayesian logic on the underlying probability. So the coin is at the bottom down here. Whenever it flicks, it turns on, and you should see it like slowly train. And yeah, so it's kind of honed in here, and then it'll reset, and we'll see it train again. Each time it flicks it, yeah, so this is a very high probability. All right. Beta distribution. Okay. Now for the meat of it. This is the coolest thing I've written, probably. This is a bunch of different computer science sorting algorithms on LEDs. If you could dim the lights. So feel free to sort of give it a minute, and then we can start to guess what algorithms we're looking at here. It's a bunch of different ones. I can also start to take questions at this point while this is going, if anyone has questions. Yeah? Okay. Yeah, I cut off the dongle on the end, and I cut into the plastic, and I pulled the two wires outside, and then I crimped a connector around and attached it to this thing. You can see it right here. Yeah, so he's saying that Adafruit also sells a power supply that's 5 volts that will fit. So you don't necessarily have to hack your own. I just was in a hacker space, so kind of the jam. Oh yeah, by the way, if you haven't figured it out, this is a merge sort. And so you can see it's merging down there, and then it had recursively sorted the whole strip, and it'll do the final merge now. Yeah, PC power supply. If you're doing a larger installation, PC power supply is like one of the best ones to do. Although a lot of times they have a big fan on them, so you got to figure it out. For the one in my room, I bought like a big Meanwell power supply that doesn't have a fan, but that was like $50. But in my room, I'm powering 13 meters of these, so yeah. Okay, anyone know what this one is? This sort? So you'll notice from here to here, it's all the blues have already been sorted into that kind of bucket. And then here's everything else, and it's recursively going inside that bucket and sorting them according to some value it's chosen. Yes, and it is Quicksort. So it's actually funny because when I imagine a recursive algorithm, I see the tree kind of going at my head, but I didn't realize like, oh wait, those things have to happen one at a time. So like recursion actually looks like you just do this tiny bit, then you do this tiny bit, instead of just. Other questions? Yeah, actually, this will do worst and best cases if you let it run long enough. I don't know if we have time for that now, but I'll just let it run out. It'll do a couple different sorting algorithms, including bubble sort, and then it'll do the worst cases and then the best cases for each of them. Yeah, to make a cool full visualization. Yeah. Hmm. Yeah. I mean, if the Python takes. Oh yeah, sorry. Um, he said, "How real time is this? If my Python program hangs, will this hang?" And yeah, I mean, if you're taking a long time to compute something, you can't update it till you're done. From the Raspberry Pi out, there's not much delay. Like once it's on the Raspberry Pi, it can just send out. And I think that probably uses, like, it flushes a buffer and then does check memory access to that. But I've never actually read the SPI library, so that's just kind of a guess. But I think it should be good. Oh yeah, I built all of this at Noisebridge Hackerspace in San Francisco, which is an amazing place. If you haven't been to a hackerspace before, look one up. There's probably one in your city. Oh yeah, 1 second. Oh yeah, this one is as it's been going on for a few minutes next to me, is very confusing because there's a lot of activity. What you're actually looking at is heap sort. So heap, I mean, I've always thought of it as a tree, but you can actually see that it's also linearized. I wrote all these. It's linearized along the strip, so that this is like a tree lookup. Looks like this kind of shimmery effect down this, and it's taking off the lowest value and putting it there each time. You can really see here how this would be really bad for cache lookups, because each time it goes down this, it has to load a whole new section of memory. Other questions? Yes? Have you experimented with perhaps adding audio to match the LEDs? I haven't done that, but I think you should be able to, especially how it's using APA 102. I think if you were using trying to figure out some way of NeoPixels, you wouldn't be able to do audio at the same time. But I think you should be able to do on this. Another thing I have, I don't have a demo with that. Or I could show it. No. I want to let the sorting algorithms finish. But I have this one is the Muni one. It's a visualization of San Francisco bus traffic as pulled down from the Muni API. It sounds really cool, but buses actually go really slow. So you'll watch for like 20 minutes and like that pixel moves over there and you're like, now I feel like I'm on the bus. But, it's easy to take this and take it to anything that, any API you can hit, any sorts of data you can bring into Python, you can put on LEDs. For instance, think about this. You have a bunch of servers maybe, and you want to see if they're up. You could put a green light if they're up, red light if they're down, and then all of a sudden you're NASA, So as I said, server uptime monitor, you can do algorithm visualizations, make beautiful items, yeah. All right, so here's my final. If you're going to take a picture of a slide, this has got all the core information on it. Yeah. How am I on time? Do I have a few minutes? 3 more minutes. Okay, cool. Does anyone know this one? Oh, it just finished. It was bubble sort. Yeah. I sped up like about 10 times for the bubble sort, to save y'all, because it can get really long. Here them all. They'll all be again and sped up. Other questions? Yeah? Come to the mic. That would be nice.
So in the beginning, you mentioned you could have a variable number of lights per strip. So do you need a different schema for each size of LED strip you have?
But you say scheme?
Or
like
scheme, yeah.
Yeah. It's just a configuration. It's just an option to the scheme. So ideally, when you write it, you think that there could be different lengths of strips, and it just uses self.strip.num LEDs and uses that. So
cool. Thank you.
Yeah, because this is half the size of the one in my room in terms of number of LEDs. Yeah.
Hi, I heard you mention that you're running this with a Raspberry Pi. I'm curious if you could hook this up to just like a full desktop computer if you didn't want to have a Raspberry Pi in the chain.
So the reason I can run it off a Raspberry Pi is it has the headers. It has like actual little wires that you can control with SPI. As far as I know, my computer doesn't have that. Maybe you could get some chip that would give headers to a desktop computer, but just in terms of thinking about it, it might be smart to put it on a Raspberry Pi, because in case you fuck up the electricity somehow, do you want your whole desktop to fry? you know, just, yeah, in terms of downside. Yeah? Any questions? Well, I'll be in the hall after this, you know, for a little bit after I take down my equipment, so in case people have questions.
So much. That was great.